So I may close my video camera because I'm not sure if this internet connection here is good enough. The signal is not very strong. Okay. Hello, I was disconnected. Could you hear me?
Yes.
Yes.
And we see your screen.
Yes. Okay, good.
Front, right.
So when shall I start?
I don't know whether the chairperson is present now. Who is at the computer? I think that there is some delay due to yesterday's Greek night.
So can I start?
I think you should start. Yeah.
Okay,
So
thank
I will
you.
chair remotely because I'm still. Okay. So it is nice to welcome Pyongwon Ko from KAIST, Korean Institute of Advanced Studies. That's correct, I think.
Yes.
And he will give a talk on multi-component, strongly interacting massive particles models with U1X that is broken to Z2 cross Z3. Okay, so please take it 25 minutes plus 5 minutes for discussion.
Okay, thank you very much. Let me first thank the Georgia and the organizers for the kind invitation. And I'm sorry that I cannot attend the group meeting in person because of this pandemic. So today, the topic of my talk is multi-component sync models with U broken to C2 cross G3. Let me first give some introduction. So I think all of us are familiar with the WIMP scenario, and some of us are familiar with the sync scenario. In the WIMP scenario, dark matter number changes involves the standard model sector, like dark matter pair annihilation into the standard model particles, and that annihilation cross section determines the dark matter relic density. And yesterday there was a talk by Michael Chirelli about this. And on the right-hand side, I show the basic idea of a simple scenario where dark matter number changes occur in the dark sector only, and it does not involve the standard model sector. So for the 3 to 2 process is important. If the 3 to 2 processes are important, and then it turns out that dark matter mass is order of 100 MeV. Whereas for 4 to 2 processes being important, then dark matter mass can be even lighter, order of 100 keV. In any case, within the simple scenario, sub-G dark matter is well motivated. And one of the most prominent example in the simple scenario is dark QCD with the fast similar interaction. In this case, we have dark pion dark matter in the flavor in the representation of unbroken flavor group H, and within, if you include the fast similar interaction, there is a 5-point interaction. 3 pion goes to KK. I'm using here the same notation as in the ordinary hadronic QCD. So 3 pion can go to 2 kaons, and this can change the number of dark matter in the dark QCD sector. And also within this scenario, dark matter self-scattering can be also rather strong. So using 5-point interaction, you can solve the you can achieve the correct thermal relic density. Whereas using the strong self-interaction among the dark pions, you can achieve the large self-scattering cross-section among the dark matter particles. And this was first studied by these people in 2015. And this plot shows the viable simple parameter space in simplest dark QCD model, and the horizontal axis is the pion mass, and vertical mass is m pi over f pi, and this curve is for the correct Lillich density, and this curve is for the correct large enough surface scattering cross section for solving the core cost problem in the vanilla cold dark matter paradigm. Then overlapping region is here, and in this region actually in this region, the validity of the chiral perturbation theory for pion dark matter becomes doubtable, and this problem becomes even more serious if you include the next meeting of the chiral perturbation theory. And in this paper with Hyunmin Lee and Sumin Choi and few years ago, I introduced the light vector measure in the dark sector, such as rho measure, omega measure, etc. Then you will have additional these diagrams involving rho measure and omega measure, etc. And then we can see that the overlapping region for correct Lillich density and large enough surface scattering cross section becomes lower. M pi over f pi is order of 2 or 3, which is much lower than the original proposal by Hochberg et al. By the way, in our normalization, the normalization of f pi in the original paper by Hochberg et al. Is factor 2 larger than our case. So in our normalization, their result corresponds to m pi over f pi equal to 10. Okay, so we show that by including the light vector measure in the dark sector, we can relax the problem of unitarity violation in the dark QCD sector. So this simple scenario is, especially in dark QCD scenario, could be interesting possibility. But the present universe made of a single component dark matter may be too simplified the picture. And I think the multi-component dark matter model is interesting and important possibilities. And in case of the simple model, dark QCD scenario provides a multi-component simp, like a dark pion, dark kaon, dark atom, etc. But in a sense, this is not component because all the dark pion dark matters are related with by flavor symmetry, and they will have all the same spins, and their mass difference between the different dark mesons cannot be large, because you know that for the number-Goldstone boson dark pions, the dark matter mass scale is scales like a current Quark mass times the confinement scale. And so if you take two different flavored dark matter mass difference, delta M scale should be bounded by lambda scale confinement. This is because in order that the pion becomes a good Goldstone boson, MQ should be much less than lambda confinement itself. So we have this bound. So mass difference between different components of dark pion dark matter cannot be arbitrarily large. So, and also all the dark pion, dark kaon, they have the same spin, like they are also scalar. So in this talk, I will try to construct the multi-component simple models with different spin and also larger mass differences. So in this talk, I present the dark matter model based on U1X broken to G2 cross G3. But before the main topics, let me discuss dark matter model based on U1X broken to G3 and U1X broken to G2, respectively, and emphasizing the difference between the global and local dark gauge symmetry. And this is just a long digression on local G3 scalar dark matter model and local G2 scalar and spin half dark matter model. So this is the content of my talk. I gave some introduction, and then I will describe a Scala dark matter with the UNS broken the G3, and in-nest dark matter models with UNS broken G2 and the general random access. And then I will describe the multi-component simple models with the UNS broken G2 cross G3. So let me start with the Scala dark matter models with the UNS broken G3, which is based on these three papers. These four papers. And here I assume the UNX dark gauge symmetry with dark matter X carries a charge down all the gauge invariant and renormalizable interaction. And then this last term here is unique to the G3 current charge assignment of G3. Okay, when this phi x dark Higgs develops a non-zero wave, we still have x to the q third power. Because of this term, the Lagrangian is invariant on the G3. In fact, the global G3 model was discussed earlier than our paper by Belange et al. They consider one complex Scala which is distinguished by this mu3 term here. And then they studied various phenomenology. But however, global symmetry can be broken by gravity-induced non-normalizable operators, for example, such as this. And then the global G3x with the electron scale mass will decay immediately and cannot be a good dark matter candidate. So it's better to protect dark matter decay or stability using the local gauge symmetry. And once you introduce the local gauge symmetry that's spontaneously broken, then you will have a massive dark photon and dark Higgs, which can change the dark matter phenomenology significantly. So this is the difference between global G3 and local G3. So in global G3 case, standard model plus complex scalar dark matter X. And in this case, direct detection and the correct thermodynamic density condition say that the dark matter mass should be greater than 120 GeV. But if we consider local G3 case, we have additional particle, dark Higgs and dark photon, and that opens additional channels for the dark matter pair annihilation. So here is the semi-annihilation, which is unique to G3 model, which involve dark Higgs, H2, and also gauge boson. So diagrams without, so in the global case, you have only semi-annihilation involving standard model Higgs, but not with the G prime or dark Higgs. So this is the allowed parameter range in the global and local G3 model in the dark matter mass in the horizontal axis and the lambda hx, which is a Higgs quarter coupling. And the open circle here are allowed region for global G3. All the points satisfy correct thermodynamic density. And then if we consider local G3 case, you can have additional annihilation channel involving light dark Higgs or light G prime. So all these mass ranges are also allowed. Okay, so this shows that the phenomenology, dark matter phenomenology, can be completely different when you consider global and local dark symmetry. And also for the light media case, light G prime or light Higgs, light dark Higgs, you can have a strong dark matter self interaction, which may be a solution to the co-cause problem. And such this kind of possibility is not possible, is not allowed in the global G3 case because you don't have a dark Higgs or a dark photon. And now let me move to U1 to G2 case based on these few papers here. And here I'm trying to explain the general random access using the exothermic scattering. Exothermic scattering, excited dark matter scatters the atomic electron and kick out and get free electron, and the electron recoil energy excess is roughly the mass difference between excited dark matter and dark matter. And there are a number of papers on this kind of scenario, but most works are based on the effective or toy models where delta, the mass difference between the XDM and dark matter, is put in by hand, and you know the dark kicks. So is a typical example for excited dark matter.
Sorry,
people
maybe you should
complex Scala phi dark matter. Yes.
Maybe if you switch off the video, the voice will be better because we lose the connection. Sorry.
Yes.
Okay, thank you.
You don't hear me?
We do hear, but the voice is disappearing from time to time. So
Hello?
if you switch off video, it might help.
Yeah, I could. Yeah,
So turn
probably
off
have
your
the
camera.
quality.
Yeah.
The quality of the sound. You are muted, Pyongwon. You are muted.
You are muted and the video is still on.
So did you?
Yes, perfect.
Okay, good. So the typical model for excited dark matter in the literature is something like this. You consider complex Scala, for example, dark matter here, and then you introduce dimension 2 operator that split the mass between real and the imaginary part of phi. Mass spreading is generated by these dimension 2 operators, and then also people consider this complex scalar coupled to the dark photon A mu. But if this dimension 2 operator actually breaks the local gauge symmetry explicitly, although softly, so the theory is not really consistent. So we introduce the mass gap using the Claus-Wilson mechanism. So this is a G2 scalar dark matter model. You have a dark phi and complex scalar dark matter X. And you can also consider fermion case too. But let's first consider scalar dark matter phi and X case. And then we write down all the possible gauge invariant terms, which is listed here. And last term here breaks the U1 symmetry to the U1 dark symmetry to the G2 after phi develops a non-zero BEP. You have a symmetry X going to minus X from the last term here. And then from here, you can consider kinetic mixing between dark photon and standard model gauge boson, etc. And for the Gino-Lanton case, we find that the XX dagger annihilation into G prime, going to G prime phi, this diagram is in P wave, so it's not strongly constrained by CMB constraint. So we assume this term is the most important for the summary density calculation for the complex scalar dark matter. And on the right hand side, I show that the G prime mass and the kinetic mixing which is consistent with correct thermodynamic density as well as the number of events that can explain the general Anton excess. So I think this light dark matter, such a light dark matter order of 100 MeV, that pair annihilation into the in the P-wave channel. This is something new that is allowed. That is possible only if you include dark Higgs boson in your model. So this is a P-wave annihilation cross section for this channel. Likewise, you can also consider fermion dark matter, excited dark matter model. In this case, from our charge assignment, you can write down this term, which break the U1 to G2 after phi development under BEP. And then you have a G2 fermion dark matter, excited dark matter model. And in this fermionic dark matter case, the P-wave annihilation can occur through this two diagram, chi-chi bar going to phi-phi through the phi exchange in the S channel or chi exchange in the T channel. And this is a P-wave annihilation. And in this plot, I show the allowed region for mg prime and the epsilon parameter space for different dark Higgs mass. So dark matter mass is order of 100 MeV again. I mean 10 to 100 MeV here, but the dark Higgs mass is below 10 MeV. And here the dashed line is we showed that this dashed line region because this triple lambda coupling, triple phi coupling here becomes non-perturbatively too much strong. But this solid line region, you can explain general Anton excess as well as the correct relative density. Again, this P-wave annihilation is possible because we have included dark Higgs in the model. So both for scalar dark matter and the fermion dark matter, we can have a P-wave annihilation so that we can avoid a strong CMB constraint on the dark matter annihilation in the early universe. So so far I introduced U1 to G2, U1 to G2 and U1 to G3 dark matter model separately. Please remember that for G3 case, only scalar dark matter is possible. But for the G2 case, you can have both scalar or spin-half fermion dark matter. So now I come back to the main topic of this talk. It's a multi-component CMP model based on U1 to G2 plus G3. So yes.
5 minutes left.
Yes. So we have scalar X and scalar Y and the dark is phi X with discharge assignment. And then because of this charge assignment, you have this last terms listed in the last line of this equation. And after phi develops non-zero web, you have this remaining symmetry, which is G2X cross G3Y. Also, you can replace this X by fermion psi. And by the same token as before, we have the model becomes G2 psi cross G3Y. So in the analysis, we will assume both X and Y are scalar bosons, but the fermionic case will be similar. So these are new Feynman diagrams that contribute to the XY relative density calculation. And here is a general consideration. So here, dark matter stability of X and Y are guaranteed by unbroken G2 cross G3, even in the presence of a non-normalizing operator. And X can be scalar or spin-half. Fermion Y is a scalar. And dark matter density, sum of these three components, is determined by the number changing process in the dark sector only. So it's a kind of a simple model. And in order to have a sizable omega X, we have to keep this XX going to YY star negligible. Otherwise, omega X will be diluted away into omega Y. And then we set up Boltzmann equations for XR, XI, and the Y and the G prime, which is a light mediator in our case. And G prime always decay into YY star, etc. So we will have a 3 dark matter candidate in our model. And for this 2 mass hierarchy case, we have a 2-component scenario. Xi and Y becomes a dark matter. And if we consider this mass hierarchy, then we will have a 3-component scenario because XR, lifetime of XR will be also very, very long enough to be a dark matter candidate. And this is a 4 benchmark point, which we M prime has 200 MeV and MH prime is much heavier than other dark side particles, etc. And then we choose 1, 2, 3, 4 different cases. And then we consider the Boltzmann equation, etc. We impose necessary various phenomenological and theoretical constraints. And this is this shows the allowed region in the MG prime epsilon. This blue dot here is the benchmark point case 1, which survives all the various constraints. Okay, and then this is again allowed parameter region in case 1, 2, 3, 4, and then this is the result for the yield of the YX and YY, etc. in the case 1, 2, 3, 4, and we can see that we can have a sizable YY and YX here. So this is the kind of summary table. Table 2. Here for the all the decay as 1 and 2. And in the one, we have about 24% of dark matter from Xi and 76% from the dark matter Y. Okay, and for case 3, for example, we have XR becomes around 19% and XI becomes 20% and Y becomes around 60%, etc. So for this particular choice of oops. So this particular choice of parameter space for benchmark point, we show that the 2-component or multi-component simple scenario is possible. Jan, hello.
Yes.
Yes.
Okay, so
you should come to an end because time is up.
Yeah. So okay, good. So this table 2 and table 3, I mean, you can see the paper for the details, but anyway, table 2 is a simple summary of my talk. So in particular parameter space I choose, we could achieve that the 2-component or 3-component simple scenario within the dark gauge model based on U1 broken to G2 cross G3. Okay. So and if you can also do the same thing for the fermionic G2 model. So we can have a multi-component simple model with the 2 different spins. So let me summarize my talk. So here I discussed the local G2 and G3 dark matter models, and local G2 model is a consistent model for XDM coupled dark photon, and the mass gap between excited dark matter and dark matter is generated by dark Higgs mechanism. And having dark Higgs opens a new window for light dark matter model without conflict with the CMB bound on the S-wave annihilation, since one can have a pure wave annihilation with a dark Higgs component. For the local G3 case, we can have a richer phenomenology than the global case because of dark photon and dark Higgs can play an important role in the thermal elegantity and the indirect detection of dark matter. And also dark Higgs can play an important role for unitarity and even for the Higgs inflation, which is discussed in this paper. And for the UNX2 broken jet crosses dark matters, this is a natural setup for multi-component dark matter, where dark matters are stable because of the unbroken dark age symmetry. And we show that the two or three component scenario can be realized in this setup. And different dark matter species can have variously different masses, and even they can have different spins. So this situation is completely different from dark QCD simple case, where one cannot have vastly different dark masses. One downside of this model is that it's difficult to find direct or indirect dark matter detections, and we may need a very good new idea. Thank you very much for your attention.
Thank you very much, Pyong-won, for your interesting talk. Is Konstantinos there in the room?
I'm here, yes.
Okay, so take over the chairing. Thank you.
Okay, thank you also. Are there any questions?
Yes, please.
Who is? Who is the person? Huh? Yes, please, we are listening to you.
Yes, yes. What is the question?
Is
Excuse me. I'm sorry, I cannot hear the question.
Can you speak closer to the microphone, please? We cannot hear the question.
Do you listen to me?
Yes, I can. I can hear you.
Multi-components, dark matter, the direct detection is the same with the one component dark matter. We have the same result from the xenon or the other result.
Excuse me, could you say again? I'm sorry.
For the multi-component dark matter,
Yes.
there are the same limits from the direct detection as in the case of one component.
I think that we have to rescale the constraint on the direct detection because certain mass of dark matter, one dark matter mass component make a small component of the relative density. So I think that depending on the how much the portion of the depending on the portion of the dark matter, you have to rescale the constraint on the direct detection constraint. But in our case, the mediator between the standard model sector and dark sector is either very heavy or very weakly coupled. So in practice, we can ignore the constraint from direct detection constraint.
Okay, thank you.
Do I answer your question?
Yes, okay, thank you very much.
Okay, sure.
Other question, we can proceed in the next talk. Huh?
Mm-hmm. Ah, yes.
Thank you very much again.
Mm-hmm. Thank you.
So let's proceed to the next talk from Professor Travis, I think.
So I'll stop sharing.
Professor Travis, okay.
Morning. Let me try to share my screen. I tried before, but I didn't have the. Okay. Share here. Hold on. Okay. You should be able to see my screen now. Is that?
Yes, that's fine.
Let's go in the page to talk to tell the title.
Yes. Okay. Yeah. Here we are.
Where is the title?
Here is the title. Okay.
So the next talk is from Professor Tetradis from the University of Athens. The title of the talk is Entanglement Entropy in Expanding Backgrounds.
Thank you. Good morning. First of all, thanks for the opportunity to present this work at this nice conference. This is work that was done with Dimitris Diataganas at the University of Athens and supported by the Hellenic Foundation for Research and Innovation. The title of the talk refers to entanglement entropy in expanding backgrounds. And actually, my interest in this comes for the possible application in cosmology. Even though I don't have specific ideas on how this could have any phenomenological consequences. It's just the beginning of thinking about this problem. Basically, what I'm going to discuss here is entanglement entropy in theories on backgrounds which have time dependence. Okay, with possible application to cosmology, and that's why I'll be interested in backgrounds described by the FRW metric with an arbitrary scale factor, any scale factor, which would include, for example, de Sitter space, flat slicing. So basically, what we're interested in is the quantum entanglement between two regions, I call them A and B, which are separated by an entangling surface, a surface script A, which is the boundary of the region A, let's say, separating it from the region B. Classically, I'll assume that there's no contact between the two regions, but quantum mechanically, there is entanglement between the two regions. And there is a measure of this entanglement, which is called entanglement entropy. Basically, the way you compute that is you have to compute the reduced density metrics for the region A. Basically, this means that you have to integrate out or to trace out the degrees of freedom in the region B. And this will give you a density matrix. Even if you start with a pure state for the whole space, the density matrix, this reduced density matrix will not correspond to a pure state. It will be density matrix for a mixed state, which will have non-trivial von Neumann entropy, which is what is characterized as entanglement entropy. And this is a measure of how strong the quantum entanglement is between the regions A and B. Now, this is a problem which is difficult to address and to solve in a brute force way, because this tracing out of region B, okay, it's easy to say it in 3 words, but in practice to actually perform the calculation is quite non-trivial. And that's why what I'm going to use here is the holographic approach, which gives a shortcut to this calculation for theories which have holographic duals. So basically, for theories in which there is a duality between an asymptotically ADS space in 1 dimension higher and a theory which lives on the boundary of this ADS space. In this case, there is a procedure, there is a recipe, conjecture, if you want, by Ryu and Takayanagi, which gives you a straightforward way to compute this entanglement entropy. Now, basically, what we'll study is the entanglement entropy for a conformal field theory, which is confined within a part of the ADS boundary, which is within this entangling surface script A. Okay. Now, the recipe says that if the boundary is static, all you need to do is to find a surface which starts from this entangling surface on the boundary, it hangs into the bulk, and to minimize its area. And actually, the entanglement entropy is proportional to the area of that surface. This is a picture that's taken from this review by these people, and it gives you a pictorial idea of the construction. Basically, here's ADS space. There's the boundary, the green surface. The yellow is the region B. The outside is the region A. There's an entangling surface. And there's a minimal surface which starts from the entangling surface. It hangs into the bulk and it's minimized. It's the area of this minimal surface that's proportional to the entanglement entropy between produced by the entanglement between A and B on the boundary. So this is the recipe for the static case. Time-dependent case, which is what we're interested in, generalization of this conjecture, given by these people here, Hubeni, Ranjamani, and Takayanagi in 2007. Basically, it says again, you need to extremize now an area, but there you have to allow for extremization with respect to the time-like coordinate as well. I'll give you an explicit formula to get the idea of what this calculation entails. Now, what do we expect? I mean, this is an interesting problem because, you know, to my knowledge, it was addressed some 10 years ago by Baldacena and Pimentel for the case of the sitter space. And basically, the expectation, which I think generalizes to the case of an FRW, a general FRW metric, is that in this entanglement entropy would have this kind of form. It would involve terms which could be divergent. And that's why there's a cutoff, a UV cutoff epsilon. In general, the entanglement entropy is UV divergent because when you have an entangling surface, there are degrees of freedom which are localized on either side of this entangling surface. And the entanglement is very strong, very close to the to the surface between degrees of freedom that live on either side, and that's why you always get a divergence, which has to be cut off by a physical cutoff of the theory. Okay, that's why these expressions here depend on epsilon, which is this UV cutoff. There's a term which is proportional to the area of the entangling surface divided by this cutoff square, the divergent term. There's a logarithmic divergence with a coefficient C2. And there's also a contribution proportional to the logarithm of the area of the entangling surface. These are the terms that you would expect in the static case. In the time-dependent case, you would expect extra terms, something that would be proportional to the area and the logarithms of the cutoff. And then what I find the most interesting is something that's proportional to the area with a coefficient that would be 0 in the static case, but now brings in information about the expansion. And this is a term that you know, I would like to compute or to show you how it comes up. Then there are constant terms which are not, you know, that don't depend on any of the physical parameters and, you know, just pure numbers, and I have included them here because these depend anyway on the choice of the cutoff. Okay, I'll go quickly because we don't have too much time. Basically, here's what you do in practice. And I'll give you the example for the case of a boundary with an FRW metric, which is spatially flat. So I have D+2 dimensional ADS space. It has a D+1 dimensional boundary. And I have arranged by slicing appropriately using coordinates that introduce an appropriate slicing of ADS space such that the boundary metric is not just a standard flat metric that you know, has been studied a lot, but a non-trivial metric, which is actually an FRW metric in 3+1 dimensions. And you can see, you know, this is a metric, what's written here is a metric of the bulk space, which is pure ADS. You put this into any program that computes all the curvature invariant and so on. It solves the Einstein equations with a negative cosmological constant. This is ADS space in a certain slicing. In the slicing set, there is a coordinate Z, which I'll call the bulk coordinate. The boundary is located at Z = 0. Okay, and this metric here actually is what's called the Pfefferman-Graham expansion, which is an expansion on this bulk coordinate Z, which includes powers of Z and logarithms of Z as well. But I won't get into the details of this. Basically, what I want you to observe is that if I set Z = 0, this capital N becomes A of tau, a scale factor. Capital A becomes again A of tau. So if I put these things in here, you can see that I get minus A squared d tau squared plus A squared times the volume of the spatial part. So basically, when I go to Z = 0 at the boundary, this metric produces a boundary metric, which is the FRW metric with flat spatial part that I want. And this is an exact solution of the Einstein equations for a bulk ADS space. A of tau is arbitrary in this, and this is important because this, I think it's an interesting part because this is, it gives you quite a general picture. Now, usually what you find is a parameterization of the bulk ADS in simpler coordinates where you get a simpler metric, like in Poincare coordinates. Here is the ADS in Poincare coordinates. What's important, what I'm saying, which is a non-trivial thing, is actually the change of coordinates between the previous metric and this one. They describe the same space, but in different coordinates. And there's a relation between these coordinates, t and zeta, that I have here. This is a Pfeffer-Graham coordinate as well, but for this Poincare parameterization. And the coordinates z and tau that I used in the previous transparency. And I know the exact relation between the two. This relation has a singularity, which tells me that actually this change of coordinates applies to the region within the horizon of the boundary metric, the cosmological horizon of the boundary metric. Okay, then, as I said, I want to compute an extremal surface, which is anchored on the entanglement surface on the boundary. On the entangling surface on the boundary. This entangling surface, I fix it to have, I take a spherical one with a comoving radius, capital R. And then what I need to minimize is an area which I can derive this expression from the bulk metric that I introduced before. And you can see, okay, rho is a radial coordinate along the boundary. Okay, it starts from 0 and it goes to capital R. Tau and z are these coordinates that were introduced in the metric for the time-like coordinate tau, and z is the bulk coordinate. And I have to minimize for these two functions in order to find this extremal surface. And I need some boundary conditions. And the boundary conditions are that when rho becomes r, first of all, z becomes 0. So basically this says that I start on the boundary from the entangling surface. And also this time-like coordinate, when I am on the boundary, it takes a fixed value, which is what I call the time of the dual theory. It's the time of the FRW metric on which the dual CFT lives. Okay, so this is a well-defined problem, apart from the fact that this expression here is divergent. I get a divergence is when I approach a boundary, there's an infinite volume, ADS volume there, and this causes an infrared divergence in this expression, which actually corresponds to the UV divergence of the dual theory. This standard thing in this ADS CFT correspondence, and it's the basic of what's called the holographic normalization. Okay, so I impose a cutoff on this bulk coordinate z. This is the recipe. It says that I have to go in, this is the logic that I adopt. I have a Pfeffer-Graham parameterization, and I impose a UV cutoff in the bulk coordinate z. This is the physical cutoff of the theory. And I have to do that for the particular coordinates in which the metric has the form that I want, the FRW metric. So I have to cut off this integral at z equals epsilon. And then if I do that, the entanglement entropy is given by the area of this extremal surface multiplied by something which brings in the bulk Newton's constant. Okay. This sounds like an extremely complicated calculation. Of course, if you think a bit about it, you say, well, why complicate things so much? Go into clear Poincare coordinates, or the extremal surface is a geometrical object, so compute it in these coordinates. You don't need to make your life difficult. Actually, in this particular case, this calculation was the first one done by Ryu Takayanagi, so you even know the answer. So where's the problem? Well, the problem is that in this introduction of this UV cutoff, because this UV cutoff is supposed to be a physical cutoff for the dual theory on this background, and you need to impose your UV cutoff not on these Poincare coordinates in this particular example, but in this coordinate here, z, Pfeffer-Graham coordinate z, in this parameterization here. So basically, the non-trivial part, which is what requires the change of coordinates, the relations between the two sets of coordinates, is the relation between the two UV cutoffs. You can do your calculation here. You have to impose a cutoff on the coordinate zeta, but then you have to change this into a cutoff for the coordinate z. This is the physical cutoff that you need to impose. I won't bore you with the details of this. Basically, the area is given by this expression. This is a Ryuta-Kayanagi result for the in Poincare coordinates. But this cutoff epsilon imposed on the coordinate zeta, I have to relate it into the cutoff epsilon on the z coordinate. And I use the relation between the two sets of coordinates that I showed you before in order to derive this expression. And you can see that the first, the leading order correction between epsilon, zeta, and epsilon, it just says that one is rescaled with respect to the scale factor with respect to the other. But then there's a non-trivial correction that goes like epsilon squared and brings in the Hubble parameter, which is a prime over a squared. This tau that I'm using here is the time on the boundary. It's not temperature, it's the time on the boundary. I ran out of letters, so I had to use tau to parameterize time on the boundary. So this is the Hubble parameter. This is conformal time, this tau. And this is the Hubble parameter, and this is the relation between the two cutoffs. So basically, what this is saying is that the UV cutoff of my theory, I fix it to be constant. This is epsilon. Let's say this is the Planck scale, for example. The Planck scale, if it acts as a UV cutoff on an expanding background, it's something that doesn't get redshifted. It's something that stays fixed, even if the background expands. And this is a physical cutoff that I have to impose in all the calculations. Now, if I wanted to rephrase the problem in terms of static coordinates, well, I have to introduce a different cutoff that will include the expansion, will be related to the first one through this scale factor, plus this extra correction. Okay, do the calculation then, and you expand in epsilon. What you find is this answer here. This is the answer. Basically, it tells you that this integral, which depends on the cutoff and times a constant, it gives you an entanglement entropy. It has this form here. It has a term that goes 1 over epsilon squared times a squared r squared. R is the radius of the entangling surface, the comoving radius. A times r is the physical radius. A squared r squared is proportional to the proper area of the entangling surface. So basically, this is the generalization, the obvious generalization of the static result. The entanglement entropy is proportional to the area of the entangling surface, divided by the UV cutoff of the theory. This is the leading divergence that you always find in these calculations of entanglement entropy. Then there's a logarithmic divergence with a coefficient which is actually related to the central charge of the dual CFT. But again, here what appears is this combination A times R, the physical radius. Then there's a constant. We won't be interested much in this. And in red is a new term, which tells you that there's a contribution that is proportional to the entangling surface times the Hubble parameter h squared. This would be 0 in the static case, and it's the non-trivial contribution that comes in because of the expansion. Similar results you can find in 2 and 1 dimensions, spatial dimensions for the boundary. In 1 plus 1 dimensions, you find logarithm of epsilon over 2 times the physical length again, which is a generalization of the standard result for 2-dimensional CFTs. Okay, so this is the main result that I wanted to show you. Now, the generalizations of this, I can make the boundary, in what I presented up till now, the boundary was spatially flat. I can introduce curvature as well with a k which can take value 0 plus or minus 1. And R0, I have to introduce an R0 here since I've normalized everything with respect to the ADS length in this calculation. Now, the scale of the spatial curvature appears explicitly as this R0 here. And I can repeat the calculation. I won't bore you with the details. Basically, the divergent integral now gets the same terms that you had before, plus a term that brings in the curvature. So there's another term which is proportional again to r squared, and I can multiply and divide by a squared, so I can get the area of the entangling surface. And now it depends on the curvature. So this is a generalization of the previous result. Now, next thing, I would like to introduce a mass scale in this problem to see how this is changed if I move away from the conformal result. To break the scale invariance explicitly, it's difficult because you need to modify the bulk theory now. So it's a non-trivial calculation, something for the future maybe. The simplest thing is to introduce temperature as a new scale. And for this, the procedure is standard. Basically, you have to introduce a black hole in the bulk. And the Hawking temperature of that black hole is identified with the temperature of the dual CFT that lives on the boundary. Now, in 2+1 dimensions, which is what is included in the published results, the bulk for a 2+1 dimensional bulk. Basically, what I need to use is the BTZ black hole. Actually, it's not exactly the BTZ black hole because I don't impose a periodicity on the phi coordinate, but all I need is a bulk horizon in order to have a notion of temperature. And this bulk horizon appears even if phi is not periodic. So this is a bulk metric. I can again repeat the calculation as before. Now, so basically I can have this +1 ADS space, local ADS space now written in some coordinates such that the boundary metric is has this scale factor, this expanding scale factor, but there is also a black hole in the bulk. There is at least a bulk horizon characterized by this parameter mu. Okay, these are complicated expressions. Basically, at z equals 0, I reproduce what I wanted, and I know the transformation between two sets of coordinates. The standard coordinates, let's call it partial coordinates that I've written here. And these coordinates in which the boundary metric is has this scale factor. And I can do things, first of all. I have to, well, there's one interesting observation that tells me how this boundary CFT behaves or how it depends on the scale factor. If I know the bulk metric, I can compute the stress energy tensor of the dual CFT on this non-trivial background through the techniques of holographic normalization. I won't give you the details. Basically, I can compute the stress energy tensor of the dual CFT. It's diagonal. Its 0, component is this, and this is the other component. This one gives me the energy density. This one gives me the pressure. And you can see that, okay, these terms, terms are quantum effects, which actually make the trace of this stress energy tensor non-zero and give me the conformal anomaly. But what I'm interested in is the first term, the term proportional to mu. And you can see this dependence mu over a squared. This mu, you can see proportional to the Hawking temperature of the black hole. Mu is proportional to Hawking temperature squared. This theta 0 for theta, I use theta to denote the temperature, the Hawking temperature of the black hole. Basically, this is telling me that this construction leads to a CFT thermalized at the temperature theta 0, which is equal to the Hawking temperature of the dual black hole, yes. But this has to be redshifted by the scale factor if I have an expanding background. So this tells me something very intuitive, that the dual CFT is a thermalized CFT at the classical level, plus some quantum corrections that I don't care about. And this dual CFT has the correct energy density and pressure that get redshifted by the expansion. Okay.
Excuse me, you have 10 minutes here.
10 minutes?
Yeah.
Okay, good. Yeah, I think that's enough. Oh, so basically now, I can compute Nakban entropy by computing the minimal area, the way I've done before. Now I have, since the boundary CFT is 1+1 dimensional, I can take a spatial, a segment now of length 2r. Now I can do the calculation in the simpler coordinates, what I call Schwarzschild coordinates. This was actually was done already in 2007, and this is the result for the entanglement for the area of that minimal surface, which would give me the entanglement entropy. And this is a standard result that reproduces what was already derived in 2004 through a brute force calculation by Calabrese-Ricard. It's a celebrated result, which is reproduced correctly by this holographic picture. Now, I can generalize this if my CFT lives on an expanding background or a time-dependent background. The result is what's written down here. Basically, all it says is that you have to make your cutoff absorb the, you define the cutoff you used in the previous result has to be related to the physical cutoff in the picture with the expanding background divided by the scale factor A of tau. And then if you put that into the previous expression, you get these expressions here. Actually, the second line is more intuitive. Basically, what it's saying is that you have, basically what appears here is θ0, the Hawking temperature divided by A of tau. By what I argued before, this is the physical temperature redshifted by the expansion, okay? And so this combination appears, and what I call theta is θ0 over the scale factor, is the physical temperature. And then in here, I can multiply by A and divide by A. θ0 over A is the physical temperature, and A times R is the physical length of the segment, which is the co-moving length R times the scale factor. So it's a very intuitive result, which tells me how all this gets generalized non-zero temperature. Now, what not been published yet is the same calculation, but in 3+1 dimensions. Here it's difficult to compute the computation for a spherical entangling surface. What can be done is the entanglement entropy for what's called the strip geometry. So basically, the entangling surface is not spherical, but is just an area of fixed width on the boundary. Now, again, I won't give you the details of this, the final result, because some interesting properties that I would like to point out. Basically, here you have, okay, this can be computed and comes in a compact form. If you take the width of the strip, if you send it to infinity, in that limit, the minimal surface sticks onto the horizon of the bulk black hole. I'm doing this calculation at non-zero temperature. So now I have a bulk black hole, which in this case, it's a planar black hole. It has a horizon. When I take the width of the strip to infinity, the extremal area touches that black hole. It just, approaches very close, it sticks to that bulk horizon. And then I can have an explicit result. Now, in this result, I have the scale factor. L is the width of the strip. L tilde is basically the length of the two spatial dimensions perpendicular to the strip, which are infinite, but here again, I've just written them in order to regulate the expression, okay? And ZH is how far into the bulk the extremal surface extends, and actually it extends up to the location of the horizon. So this bulk coordinate ZH takes a specific value, which is fixed by the mass of the black hole, and which is what defines the Hawking temperature. So with all this, I can have an interpretation in terms of the thermalized CFT with an energy density and pressure that scale with A to the fourth now. This is the proper redshifting for the energy density for a CFT, a massless theory in an expanding background. It's standard in cosmology. It's radiation dominated era, if you want. And final result for the entanglement entropy is given here. Basically, what I get is the same term that I had before. Now, in the strip surface, there are no logarithmic divergences for a strip entangling surface. There is a term that goes over 1 over epsilon squared times the area of the entangling surface. Then there is a term that I found before, which is again the area times h squared. This is a term that's interesting. And then there's a term that's again goes like area times t squared. And then there's a term that goes like a volume factor, goes with a volume factor. You can see here a cubed times L tilde squared times L. This is the proper volume. So this is a volume factor. This tells you that there is a volume contribution to the entanglement entropy. But if you look carefully, you will find that it's multiplied by the effective temperature T cubed, and this is nothing but the thermal entropy of the CFT. So basically, it is saying that in the limit that I'm looking at things, when everything is dominated by the temperature, basically what I compute here as entanglement entropy is nothing but the thermal entropy of the CFT, because now basically the reduced density matrix dominated by the thermal effects. So this volume factor is not something new related with quantum entanglement. It's just the entanglement that I expect from a thermalized CFT for very high temperature, which corresponds to the thermal entropy. Okay. I'm running out of time. What I want to say very briefly is that there are various cross-checks of all these results. They agree with what was expected by the paper by Maldacena and Pimentel, and various other calculations, brute force calculations that we found in the literature. And with this, I come to the conclusions. Just to finish, I want to point out what comes out of this calculation. Basically, what you find is that if you have an expanding background, the entanglement entropy has the same form, the divergent terms have the same form as in the static case, but now what comes in is the radius or the area of the proper area. It comes the physical radius or the proper area of the entangling surface. Okay, so this is the first expected, let's say, generalization. In this theory that we looked at, which is dual to pure ADS, which is the n equals 4 super Young Mills, in principle, one would have another logarithmic divergence, but this is absent for this particular theory. It should be there for more general theories, but it cannot be seen in this particular case. Now, you get a contribution from the spatial curvature, which again is proportional to the proper area. This is what I showed you before. What's most interesting in this is the finite term, which involves the expansion rate. This accounts for contribution to the entanglement entropy, which from regions which are not confined in the vicinity of the entanglement surface. The degrees of freedom that live very close to the entangling surface give you the divergent contributions that go like 1 over epsilon squared or log epsilon, so on. Now, this finite contribution is supposed to arise from entanglement from further away from the entangling surface, and that's why it seems more interesting to me. One interesting observation is that it goes like scale factor squared, which basically means that it's the same for an evolution for a shrinking or expanding background. If you think about it, probably this means that the entanglement is enhanced when the entangling surface moves within the space, because there are degrees of freedom that cross from region A to B or the other way around, and this enhances the entanglement. The finite term that we that we found here is proportional to the area, not to the volume. So basically, even though this entanglement is not confined to the region of the entangling surface and accounts for entanglement from larger distances, it's never strong enough to become a volume effect, at least within the theory that we looked at here. All this, as a final remark, all this was done for an arbitrary scale factor. So basically, you can apply it to any cosmological background you want. If you assume that this applies to the cosmological expansion, which is driven by an equation of state with a parameter W, basically what you find is that when the time goes to 0 at the Big Bang, let's say, this contribution diverges like 1/t squared, 1/time squared. So basically, at very early times where everything is compressed, this entanglement grows, it explodes. Basically, the physical volume shrinks. So adjacent points become more and more entangled in this limit. I think this is a natural expectation. Of course, all this is interesting, but this finite contribution can never exceed the physical cutoff that gives you the divergent contribution that's cut off by the physical cutoff of the theory. So basically, it's difficult to disentangle this contribution to the entanglement from the divergent contribution. I think this is the what makes it difficult to find an implication of this term, a consequence of this term. Again, though, I think it's a interesting term. As I said in the beginning, this is just a calculation to compute it and to see what comes out. So basically, what comes out is something that goes like scale factor squared, Hubble parameter squared times proper area of the entangling surface. What kind of physical implications it may have, if any, it's not clear to me yet. This is something that we have not explored yet. So I think this is this concludes what I had to say, and I would like to thank you for your attention.
Is there any question, comment, suggestion?
Hi, can I ask?
Yeah, of course.
Yes, Nico, thanks for the interesting talk.
Thank you for listening.
Can you maybe go to the first slide in specially flat FRW? Okay, maybe this is a naive question, but I see here, yes, you have something that includes something like a scale factor, this capital A, but then this N, this could be something like the light speed, and it seems to vary here. Is this the case, and what is the physical significance of this? Maybe it's this is well known, but peculiar to me.
I haven't thought explicitly in the terms that you're posing it, but this is just pure ADS. So I don't think there's any problem with the light speed or whatever. It's just written in weird coordinates. So
no, I agree with you, but you would like, I guess, to say something about, yes, FRW metrics and cosmology. That's why I was...
No, the FRW metric is applies to the boundary. Now, in the bulk, we just have pure ADS in weird coordinates. That's all it is. So I don't expect any complications with respect to the speed of light or whatever. Whatever holds in, and it's of course coordinate invariant, right? In ADS should apply to this as well. Even though, I admit that I haven't thought about this question that you posed, how I can check this in these coordinates, but I don't expect that there should be a problem with causality or whatever. It's just pure ADS.
Okay, so it's one really cares only about the boundary, the FRW, yes, metric in the boundary. So this is not that relevant. Okay, good. And then again, this is very general, and I completely acknowledge that there's difficulties with defining entanglement entropy in quantum field theories where you have infinite degrees of freedom and so on. But in the end of the day, whatever quantity should be finite.
There's somebody else speaking, and I can't hear you very well. Yes. Can you repeat it?
So, of course, there are many difficulties when one considers quantum field theory, when there are infinite degrees of freedom. But in the end, some definition of entanglement entropy of any physical quantity should be finite. Maybe one could think of, let's say, entanglement entropy differences with respect to some reference, I don't know, state or configuration. Are the divergent terms physical? Do they carry some unambiguous meaning, or is it just the constant term that one should really be caring about when one removes all these divergences? What is the unambiguous? Yes, go ahead.
I think the divergent terms are physical, and I think that's the problem. Because, and this is standard in calculation of entanglement entropy in statistical systems, let's say in 2 dimensions, so on. Basically, there's very strong entanglement with degrees of freedom with very short wavelengths, which live very close to the entangling surface, left and right of that. So these are very strongly entangled, and they give an infinite contribution if you don't cut off the theory in the UV. Now, for any true physical system, there is a UV cutoff, a physical cutoff, depends on the system. And this is actually what appears in the expression for the entanglement entropy. And that's why I was saying that these finite terms, it's hard to disentangle it. I mean, you can disentangle it in terms of the dependence on the radius, for example. I mean, if you have the whole function, you can isolate that contribution. But the problem is that the divergent terms are not unphysical. They are physical, they're there for physical systems. They're cut off by the physical cutoff of the theory. So if you had some lattice, it would be the lattice spacing, or if you had, I don't know, some crystal, it would be, distance between atoms or whatever. There is some physical cutoff there, which affects the entanglement entropy. And this is standard in brute force calculations. Okay, you have to put that in, and it's different every time. So that's the difficulty in the interpretation of this finite term. Of course, this doesn't make the finite term, because that could be an objection. Well, if there depends on the cutoff, how physical is the finite term now?
Yes, it
if
exactly changes.
If you have the whole dependence of the radius, you can see that term. Okay, it's a parametric dependence on the parameter. It's the dependence on the parameters of the theory that can identify the term. And of course, you can take differences between, I suppose, 2 theories, the same theory with 2 different cutoffs. I don't know, you can try to all different radii to try to isolate the interesting effect. But as I said, these are questions that I haven't thought much about yet. Up to now, we're more interested in completing this calculation.
And this brings me to my last question, if there is time, if the chairman
I don't
allows.
think there is time, unfortunately.
Okay.
There was another, sorry for intervening, but I have to keep the time from the Zoom. I think there was, sorry, you can discuss in private.
Okay,
Yeah, we can
thanks a lot.
There was one from Juan Garcia Bellido. I've seen your hand, Juan.
That's right. Hi, Nick.
Sorry for intervening, Costas, as well, Juan.
And hi, Nico. It's nice to see you also. Well, actually, some of the questions already were posed by Georgia, so I think we could go on. In fact, I'm the next one in line, so I'm happy to take on and give my talk.
Thank you.
Okay, so let's proceed to the next talk.
Thank you again.
From Professor Juan Garcia Bellido, I think, from University of Madrid.
Sorry, George or Nick, could you please give me the possibility?
How you should be able to share.
I cannot share the screen. Oh, yes, I can now. Very good. Thank you. Can you see that?
So let me announce the title: Covariant Formulation of Entropic Forces, Cosmic Acceleration from First Principles. We are listening to you.
Thank you very much. Okay, so it's a pleasure to be here. Thank you for the invitation. I think it's very interesting, and I wish I could have been there in Corfu physically with you. Hopefully next time we'll be able to. Unfortunately, the COVID has helped. So I'm going to talk about a new idea that we've been developing with my student Llorenzo Espinosa in Madrid, which is trying to understand the present cosmic acceleration that is how supernovae become dimmer than expected from first principles. And when I mean by first principles, I mean by fundamental features that appear when you take into account coherent phenomena. So for this, I will need to very briefly describe what are the nature of forces in physics. We are reduced to, of course, fundamental forces, gravitation, strong, the weak, electromagnetic. There are also residual forces, those that come out of these fundamental ones on longer distances, like the molecular forces, nuclear forces, surface tension. But then there are also collective forces, those that apply to Brownian motion whenever we have a fluid, you know, or in particular entropic forces. And I'm going to concentrate on these ones, the last ones. Okay, our proposal is the following. Entropic forces can be responsible for the present cosmic acceleration and many other large structure phenomena. This is where we will look for a confirmation of this. But for this, we need a covariant formalism of out of equilibrium phenomena in GR. And up to the moment, there hasn't been one. Okay, I will show how we develop one from some ideas from some mathematics.
Excuse me,
You will see.
just the first page. You are in the first page still.
I'm sorry, you cannot see the other.
No.
That's.
Yeah, no, it got stuck.
I'm sorry. So let me cancel this and change perhaps to stop sharing. This happens sometimes. Let me go to the PowerPoint. Perhaps in PowerPoint it's easier. Sorry about that. So you can see this. Let me try to. How about now? Can you see that?
Yes,
Can you see
Yes.
this?
that's good, James.
Very good. Okay, thank you.
Thank you.
All right, so I was describing fundamental forces, residual forces, and collective forces, and particular entropic forces. As I said, entropic forces, we claim, could be responsible for the present cosmic acceleration and many other large structure phenomena that I'll describe at the end. But for this, we need a covariant formalism of out of equilibrium phenomena in GR. At the end, we will convince ourselves that we just need quantum mechanics, in fact, quantum field theory, non-equilibrium thermodynamics, and general relativity in order to describe all these phenomena. So there's no need for physics beyond the standard model. Now, the motivation is very clear. In general relativity, we have a theory which is time reversal. If we change t to minus t, we won't see any difference in terms of the dynamics. However, most of the history of the universe is adiabatic. Actually, it's in local thermal equilibrium, although there is an error of time. So we would like to see how this irreversibility associated with out of equilibrium phenomena can be accounted for in a coherent formalism within GR. Okay, so for the moment, it's not yet there in a systematic way. Now we're used to cosmology. This is very basic. A homogeneous and isotropic universe would have this line element. If we fill it with a perfect or ideal fluid, it would just be dependent on pressure and density, and the Friedmann equations have a simple form. We will concentrate on F2 in the following. Now, it's clear that the covariant energy momentum tensor conservation gives rise to a relation between the evolution of the scale factor and that of the energy density. But this can also be derived from the second law for thermodynamics and equilibrium. I was saying the universe is mostly expanding adiabatically or in local thermal equilibrium, and therefore we can assume that there is no entropy production, except for a few cases like the Big Bang, for instance, or preheating after inflation, where there's a tremendous number of particles being produced. So we would like to see what happens when these phenomena come in. So it's simple to see from this second equation that one can derive, beyond adiabatic cosmology, the continuity equation where the scale factor evolution determines the density growth with taking into account the possible growth of entropy. If we put this together with the Friedmann equation, the simple Hamiltonian constraint in the context of FRW, then we see that there's a new force, new acceleration induced on the universe by the growth of entropy. So this is a very simple statement. Let's see how can we incorporate this in a more systematic way in GR. Okay, so notice the positive sign of this entropic force. This means that if entropy grows, we will have a positive acceleration induced by the growth of entropy. So how does this get incorporated in a covariant formalism of general relativity? So for this, we had the help of Guy Balmas and Yoshimura, 2017, where in a very nice series of papers, they propose a variational formulation of non-equilibrium thermodynamics in general mechanics. So we're going to explore this entropic forces in mechanics. Remember, we usually take the stationary action principle. We're going to supplement this with a lot of thermodynamics, which provide constraints on the dynamics. So this is a constrained mechanics, if you want, just like the rolling of a ball in some inclined plane where you impose a condition that there should be no slippage. And this defines a variational problem, a simple thing. So in a general mechanical system with canonical coordinate Q, the action is given by the integral of the Lagrangian. Here, it not only depends on this canonical coordinate and its derivative, but also in the entropy content of the system. And therefore, any variation of the action contains both a variation of the canonical coordinate as well as a variation of the entropy. So once we supply a thermodynamical constraint, which is nothing but a relation between this variation and some extra function, we'll see that this is nothing but the entropic force, then we obtain the constraint equation of motion. Notice that this is no longer zero, and this is the usual, in the context of generativity, geodesic equation, which gets modified by the presence of a force. This force is a friction or entropic force. So what's the physics of this? This, of course, has to be obtained from the thermodynamic constraint. So in particular, you remember that you usually take the Lagrangian as the kinetic minus the potential terms. So you can write the temperature of a system out of variation of internal energy with respect to entropy. And therefore, by taking this relation between Lagrangian and temperature, we see that in entropy production, so S dot positive means that this term, F times Q dot, should be negative or zero. So that means that dynamics is modified because there's extra force, and also that there is a time reversal symmetry which is broken in the system. So the generalization to generativity is straightforward. Here you have the usual gravitational part of the action. You have the matter term. Now it depends not in the canonical coordinates Q, but in the metric and the entropy, and therefore the variation of the action gets the usual terms that will give rise to the Einstein equations plus a new term. So the entropy of the second law of thermodynamics comes through a variational constraint on this term. So it's telling you that this law derives variations on the internal part of the system that inevitably should generate variations of the metric. So you can derive by substituting this here. Later on, we'll see what's the actual expression as mu. By substituting here, you see that the Einstein field equations are modified in the presence of non-equilibrium phenomena, and there is a new term that appears in the Einstein equations. So this is the whole crux of the work. No? So the Einstein equations have been modified in such a way that whenever there is entropy production, the Einstein equations are no longer the Einstein term equals the T mu. So there's an extra force. Okay, it's interesting because what the Bianchi identities implied before in GR, which was the conservation of the energy momentum tensor, now through the Bianchi identities we have a relation between the non-conservation of the energy momentum tensor and those friction or entropic forces. And we will use this, of course, to derive the acceleration of the universe. Now, in order to be more concrete, is much better, especially if we're going to go to the context of Freeman-Rosen-Walker or expanding universes, to do a 3+1 splitting of space-time is the usual ADM formalism. We have our lapse and shift functions. The lead derivatives along a normal vector now is a generalization of the time derivative. We have our normal vectors in the time slice orthogonal to the time slice in terms of the lapse, and we can derive the projection of the metric onto the three-dimensional surface as h mu. Here you can then construct the extrinsic curvature and derive the non-trivial thermodynamic constraint in terms of the projection of that tensor over that surface, free surface. The Hamilton equations are the standard ones, except that there is a new term. This will give rise to the entropic forces. And in the Hamiltonian moment constraints still are satisfied. So H is equal to 0 and HI is equal to 0, just simply from the fact that the action does not depend on the lapse and the shift. But there are terms here in the Lagrangian with respect to n that will induce an extra contribution in Hamiltonian constraint. So a very physical way of understanding how these 3+1 splitting derives specific forces onto space-time is by looking at the congruence of world lines, okay, and then deriving the Ratchet equation. So if we take a congruence, we split the derivative, covariant derivative of these normal vectors in terms of the trace, theta, the shear, the symmetric part, and the vorticity, the antisymmetric part. We could also add an extra term, an intrinsic acceleration, which will lead to 0 afterwards. Then the derivative, or the time derivative, with respect to the normal coordinate, time coordinate, of this trace is the famous Ratchet equation. Okay, so whenever we have, since this is positive for any value of the sigma field of the shear, and since theta squared is positive, as long as we don't have any vorticity, this will not change things significantly for gravitational collapse, as we will see. Then using the Einstein equations, which relate the geometric part with the energy momentum tensor and the entropic forces, then substituting this into the Ratchet equation, as long as we have the strong energy condition, so ignoring any other kind of force which is induced by some non-trivial matter. So let's assume we have ordinary matter that satisfies the strong energy condition, so radiation and matter, for instance, no cosmological constant. Then, and in the absence of intrinsic acceleration, we find a bound. Okay, this is similar to the Hawking-Penrose theorems, right? So it's interesting because there's an extra term which could be positive, as long as it's sufficiently large and positive, then we can avoid recollapse. So you can imagine a congruence of geodesics, matter is expanding. Eventually, in the absence of any cosmological constant, this would reach a maximum value, and then it would contract again. That's the theorem. However, in the presence of entropic forces, if inside the bulk or on the surface, as I will describe, there are degrees of freedom which are entangled, which are still keeping information, and therefore can backreact on the metric, it will stop the expansion and it may recollapse. As long as this is positive, you could have a contraction. You could have, you could have expansion. You could go on forever expanding. So let's see how these entropic forces appear in GR. Let's concentrate first on the matter content and afterwards on the gravity sector. So temperature and entropy in matter can be seen in a mechanical system, as I was describing just a while ago, by writing the Lagrangian as a kinetic minus internal energy, and the temperature is nothing but the variation of internal energy with respect to entropy. In the case of hydrodynamical matter, when we have an energy density, this one now depends on the metric as well as on the entropy density, and therefore the temperature is given by this expression, minus rho, the variation of rho with respect to the internal entropy density. Now, in the gravity sector, it's slightly different. For instance, we can consider both so bulk entropy driven by the matter inside a certain volume, for instance, a horizon, but we could also consider what's the entropy associated to the horizon, to the surface, and this is well known since the work of Gibbons, Hawking, and York. Okay, and this can be seen by writing a surface term. In this case, the action is given by the integral over the surface of the extrinsic curvature times the metric on that surface. And this in particular, for the case of a horizon with some symmetry, is given by this expression. And we will use this expression in the following. Now, for instance, if we take the possibility of looking at the entropy on black holes in the interior of this volume, those black holes have an entropy which can be computed, and a temperature which can be computed through the Hawking-Bekenstein formula, which first has two properties. First, the action is proportional, the entropy is proportional to the area, and the temperature is inversely proportional to the mass. But it has another aspect which is much more interesting, that all of these quantities, thermodynamical quantities, are actually of quantum origin. We still do not know the precise meaning of this temperature and entropy in terms of fundamental degrees of freedom on the surface of this black hole, But nevertheless, the temperature is proportional to h bar. So if we make h bar go to 0, the temperature is 0. Obviously, it doesn't radiate. And contrary, if we take the entropy of the black hole with h bar going to 0, it would explode. We would have a divergence. So, but interestingly enough, the action of such a entropic force term is classical. So the h bar part of temperature and entropy, it cancels in the numerator and denominator, and it's essentially an emergent phenomenon coming from the quantum entanglement of degrees of freedom inside and outside of the surface. So it's this quantum entanglement which sets the degrees of freedom on the surface of the black hole and derives and produces a term that will be proportional to T times S and will contribute to as an entropic force. Okay, let's see what happens when we consider. Sorry, 10 minutes?
Yeah, 10 minutes.
Okay, so entropic forces, of course, can be looked into Freeman-Lemaitre, Robertson-Walker. So we continue this formalism into FLRW. We keep our lapse function. Right? We compute what is the non-conservation of the energy momentum tensor in this case using the second law of thermodynamics, and we derive an equation that we had before. If we take the Hamiltonian constraint, the Friedmann-Ratchaduri equation, and I mean Ratchaduri because this is analogous to the previous expression that we had here at the bottom, you see that there is not only the usual term, rho plus 3p, okay, with a negative sign that tells you that acceleration is decreasing, so it's negative, so we will have the universe is very slowly slowing down. However, in the presence of some entropy production, this could be in the early universe or it could be in the late universe, this entropy production may give rise to an entropic force that will slow down and rather than rather than have collapse, it will just blow the whole system and it will make the universe start accelerating. So we made a concrete realization of such a idea in a scenario based on the nucleation of a bubble inside the sitter, the usual open inflation scenario, where you have in the early universe at the sitter phase, a nucleation of a bubble inside the sitter leaves inside a coordinatization of an open universe. If you have still some vacuum energy, some dynamics of some scalar field and inflaton field inside the bubble, this will drive the expansion, accelerated expansion, for some e-folds, let's call it n. And as the universe expands and drive this to essentially flatness, we can ask what is the boundary from the point of view of an observer inside this open universe as it looks back towards the surface of last scattering, for instance. So we can ask what is the observer's causal horizon, and using the formalism that you have here, the action in terms of the extrinsic curvature and the metric on that boundary, we can compute this rho h as ts over a cubed, or if you want rho a squared, as a quantity that you can compute today, which is this x naught, the deviation with respect to 1 of the total matter content over the matter content. This is going to be very close to 1. So this is going to be similar to omega k times a sine function. Now, if you take this expression x naught, it's easy, given a certain number of e-folds, given when the universe reheated, this would correspond to a certain hypersurface within this open universe, and given some time since matter radiation equality, we can compute very precisely this x naught. And this will contribute as an extra force, entropic force, into the Einstein-Friedmann equations. And this, written in the Hamiltonian constraint, written in conformal time, so what primes denote with respect to tau, we've multiplied by this constant, A naught H naught here, can be written this way. And there are exact solutions, or we can solve these with an entropic force. Notice that we haven't added here any cosmological constant. There's no need for a cosmological constant if we have this entropic force. And we see that such a force will drive the expansion in a way which is extremely similar to lambda quadrant matter. If we compare, we start at very high redshift with initial conditions in the radiation era, so right at the end of recombination, then we could follow the evolution of both lambda cold dark matter for the values of omega matter, omega k that we have, and h, the corresponding parameter of h.68. And you see that when we move towards redshift 0, there is a point that deviates slightly when the unit starts to accelerate, both in lambda cold dark matter, which happens at redshift 0.65, or in general-relativistic entropic acceleration theory, which starts at redshift 0.83. Moreover, since we have still the freedom to determine what's the number of ethyls inside the bubble, or if you want, what is the reheating temperature, still have this uncertainty, then the value of omega k is still undetermined. Now, if we take a given value of omega k, we obtain a value for the rate of expansion today, which is different from what you would expect in lambda cold dark matter. So instead of 0.68, which is what lambda cold dark matter would have predicted, we can obtain a value which is more closer to the local value that has been claimed by Rees and others. That happens relatively nearby, at low redshift, or when very near to the scale factor 1. Moreover, we can compute what is the evolution of the equation of state, the effective equation of state for such a fluid, irrespective of what is its nature, this entropic force. We can parameterize in terms of an omega k, omega of a, and therefore determine what's omega naught and omega a. And we see that this is perfectly consistent with the observations nowadays from the CMB from logical structure. Moreover, just quite interesting to observe is that when you follow towards infinity the evolution, when you take a scale factor to infinity, so as the universe keeps on expanding, you see that the universe doesn't end in the sitter like it would happen in lambda cold dark matter, but it ends in Minkowski. If you want this scribe plus for this Penrose diagram, it's actually Minkowski. And with this, I conclude. Let me summarize here. Non-equilibrium phenomena in GR can be used to describe entropic forces, collective forces, given by the bulk or the horizon or the surface terms. There is a 3+1 slicing, which gives a modification of the Ratchador equation that could prevent gravitational collapse. We derive cosmic acceleration from first principles in this case, as long as we have entropy production, and we claim that due to the actual horizon in which we are embedded, there's no need for a cosmological constant. Just simply the growth of the entropy associated with the horizon will drive the cosmic acceleration. So we only need quantum field theory to fill up the universe with matter, generativity, and non-equilibrium thermodynamics. There are multiple consequences for logical structure, and this could be a possible solution to the question. I finish here. Thank you very much.
Okay, thank you very much.
Thank you.
Any questions? Comments, suggestions?
Yes. Can I ask the question? Yes. Thank you. Very nice. Very nice talk, Juan.
Thank you, Nick.
I would like to ask one question related.
Sorry, excuse me, George, do you mind?
Approach, which
just a moment, Nick. Just a moment, Nick. There's an echo. I can ask George to.
Yeah, if we could mute, perfect. Thank you.
Now I can hear you.
Now you can hear me. Yes. I would like to ask one question on this interesting idea that you have. If you view gravity like Verlinde, gravity as an entropic force due to motions of some, is your term, probably you could also adapt your approach to this or not?
It's an extremely interesting question. I have made myself this question. I don't have a clear answer. For me, in the case of Verlinde, it's entanglement between the sitter and the rest of bulk matter, baryon matter in the bulk, in the interior, which drives or generates dark matter. In our case, it's just the opposite. So if you want, it's the presence of matter and the presence of a horizon, which is a reflection of matter. Of course, the universe is expanding. This creates a surface beyond which we have no access, therefore introduces an uncertainty, and this produces an entropy. The fact that we don't know what happens at the other side of the horizon, just like we have with a black hole horizon, is what induces this entanglement entropy, which drives the accelerated expansion. In his case, it's just the opposite. Okay, but somehow the two phenomena, the fact that entanglement is responsible for the modification of dynamics is common to both.
Yes.
In my case, I come from a formalism, general relativity, which is perfectly well posed. I'm not deriving general relativity as the effective dynamics, the emergent dynamics from the entanglement properties of that horizon. For me, general relativity is the formalism that describes how the curvature of matter determines curvature, and curvature determines the congruence of geodesics. It's the horizon which is driving a collective phenomenon, modifying this dynamics. Okay, so for me, the horizon modifies the dynamics. For him, the horizon entanglement generates the dynamic. Okay, right. So there is some connection, but it's not quite the same thing. Both are emergent phenomena. Remember
yes.
that the action on the surface that we derive, it doesn't have any H bar in it. Okay, it's classical. Even though the fundamental degrees of freedom, that which is entangled inside and outside in the bulk, in the usual Freeman-Russell-Walker, and outside the horizon, these are fundamental degrees of freedom which are entangled. Well, both are emergent, but I don't think there has been such a connection. But it's an interesting question.
Thank you very much.
Any other question? Nikos.
Yes, thanks for the talks. It was very nice. I'm trying to understand the entropy you're talking about. Is it just thermodynamic entropy or is it entanglement entropy?
It's entanglement entropy, and there are two types of contributions. You could have entropy in the bulk. For instance, you could have a particle production. Imagine right at the end of inflation, you heat the universe. On a given horizon, you produce particles. Those particles are changing your entropy content of your horizon, of your volume. And this is ordinary entropy. We can compute what's the entropy of those quantum particles. And this entropy drives, again, an accelerated expansion during preheating. This is something which we're working on right now. Okay, it's not yet published. Now, in the case of the bulk entropy, you could have other sources of entropy. For instance, we have in mind, and this is my connection to logical structure, we have in mind the formation of structure, the cosmic web. We have in mind the formation of galaxies themselves, which are rotating. They are ordered. There are arms, there are bars in spiral galaxies. Now, these induce some entropy production also for the environment. And this entropy production will give rise to very tiny accelerations. These tiny accelerations, for instance, could modify slightly the rotation curves of galaxies. You could have an acceleration induced by these entropic forces, which are changing the rotation curves of galaxies. So a little bit a la Mond, but based on fundamental principles. Okay. Now, on the other hand, in the case of the horizon, these are honest entanglement properties between the inside and the outside. So if you have a quantum field theory, you can ask, what if you coarse grain over what you do not have access to, which is beyond the horizon, what is the actual entropy associated with that horizon? And this is what we use.
Okay, one quick question, please.
Claudio.
Yes. Hi, I'm Claudio Coriano.
George, please mute.
A question. Yeah. May I ask the question? Or?
Yes, I was asking George to mute, otherwise I won't be able to hear you.
Yeah, okay. So I wanted to ask, what happens if you, for instance, you consider already from the beginning modify gravity, like, I don't know, Lovelock or something else? I mean, how does this thing change? And what eventually topological term, have you thought about it? What can they do in this context?
Both are excellent questions. The entropic collective forces are due to the quantum matter, which are inside the space-time. Okay, so in principle, if you modify gravity, you make this Lovelock modification, or FFR, no? You change the actual dynamics, how matter modifies the metric, then this will be an extra force on top of that. Okay, so they are not incompatible. They're just simply additive. You just putting that extra force on the corresponding Einstein equations. If you modify the Einstein equations because of new, more complicated gravitational dynamics, you just simply having to take into account the matter is supplemented by this thermodynamic constraint. So in that sense, there's no significant change. In terms of topology, that's quite interesting because the surface terms also contribute with an entropy. So if you have a non-trivial topology, for instance, a torus, we live in a flat universe, then this torus will contribute with a different extrinsic curvature. Remember the term for the action. H is changing, so the surface on the surface metric H will be different, and the extrinsic curvature will also be different, and it will have a different time dependence for the scale factor. So perhaps there are different solutions which we have not explored, but it's definitely worth exploring. Thank you for the suggestion.
Yeah, I just want
question.
Make sure nobody else is asking.
So,
Hello, everyone. This is Paul Frampton here.
And, hello, Paul. Nice to see you. Nice to hear you.
Yes, as I'm sure you know, at least a decade ago, I wrote with Smoot and Eason something in similar spirit, but certainly different in detail. So I enjoyed this talk. And
thank you.
My two questions are: if you write this if you think in the language of dark energy, what is your equation of state?
Yeah, I drew that. Thank you for the question.
I'm sorry, I was doing
the equation of state is different from -1, and it has a form WA that is explained by this expression. And we can ask ourselves, what is the present equation of state? Can we see the difference between lambda columnar? Indeed, we can, because W0 is not just -1, it's -0.941. That will depend on the actual value of the only parameter that appears in the theory, just one parameter, which is omega k, or x naught, whatever you choose. But also you have W of A.
Is that consistent with the dark energy survey?
It's consistent with all data. It is.
0.94, did you?
Yes, that's right. For the moment, the error, I know because I'm a member of Dark Energy Survey, and I was also part of Tank. So the error, W0 today is about 0.1. It's a 10% precision. We are going to reach with Euclid like about a few per mil, and this is where we will be able to test the theory.
I think it's already better than 0.1.
No, it's not much better.
0.02 or something. I've seen figures much more accurate. Anyway, the other question, which is more general, is have you considered trying to use these entropy arguments to make a cyclic cosmology along similar lines?
I have not thought of that. That's an interesting proposal. I never thought of that. Yeah, I'm happy to discuss this with you anytime. I don't have a quick answer for that. But thanks for making the question.
Okay, good to see you.
Let's just stop here. Is there any other question? No, I think. So let's proceed in the next talk.
Thank you. So I'll stop sharing.
Okay. Thank you again. So which is the next talk? I think it's from Juan Solá Peracuaula from the University of Barcelona.
Yes, you can hear me?
Yes, yes.
Okay. So,
please share the screen.
You want me to share the screen? Okay.
Okay.
Yes, no, it's the last question, the last talk of it. This is the last. So 11:30, we finish.
Okay. So can you see this?
So let me announce the talk. Running vacuum from quantum field theory in curved space-time, phenomenological implication, C8 and H0. We are listening to you.
Okay, very good. So good morning to everybody, and thank you for the invitation to this workshop. So it's nice to be here virtually, at least. I have been here in previous occasions physically, but this time it has to be in this virtual way. Okay, so thanks again for the invitation and for the organization. So my talk will be on this running vacuum from quantum field theory, and then some applications to these well-known tensions of the standard model of cosmology. Okay, so the guidelines of my talk are these ones. I will be talking about the vacuum energy and the cosmological constant problem, then the idea of dynamical dark energy and running vacuum energy, which is more specific than just this generic notion of dynamical dark energy. And I will try to substantiate this running vacuum idea from quantum field theory. I could say and beyond, but I will not have time to go beyond quantum field theory, although I will mention some ideas. And then I will, if I have time, I will try to apply these results to the possibility of smoothing these tensions, these H0 and sigma 8 tension. Okay, so we start from the well-known Einstein equations, in which we have this term, lambda term, the cosmological constant term. And as we know, this term, in the simplest canonical version, it should be a constant, because if we apply the covariant derivative on both sides of this equation, Einstein equations, and we use the Bianchi identity of the Riemann tensor, which basically translates into the fact that the covariant derivative of the Einstein tensor is 0, then of course this means that this is 0, the covariant derivative. This is of course 0 as well, and then we are left only with the normal derivative of this parameter here. Then if we assume that G is constant and the matter is conserved, locally conserved, then of course the covariant derivative of the right-hand side is also 0, and therefore we conclude that this derivative of lambda is 0, so lambda is constant. But as you can see, we have made a lot of assumptions here. So if we relax some of these assumptions, maybe this lambda could be something else. It could be, for example, time evolving with the cosmic time, okay? There is also the possibility that there is an interplay between the variation of the energy momentum tensor of matter and the variation of the gravitational coupling, provided, of course, that the covariant derivative of this combined term would be 0, okay? All right, so once we have this lambda, and we assume that this what it is, there are some scenarios, but in all of them, this lambda is a parameter which is somehow associated with the vacuum energy in that the matter is concentrated on the right-hand side of these equations. So if we define this quantity rho lambda in terms of lambda and 8 pi gn, then because it has dimension 4 in natural units, it has dimension of energy density, we have to interpret that this is the energy density of something. If it is not of matter, it can be called of vacuum if you want, or just dark energy. So this is the situation since 1917, right, when lambda was introduced by Einstein. It was introduced in this paper on cosmological considerations on the general theory of relativity. It was introduced basically because he wanted to solve a problem which was not that problem after all. I mean, he wanted to have the universe static because of the fixed stars, or whatever you want to call it. But of course, the stars are not fixed. The universe is not static, as it was shown later. So in principle, the primable motivation for introducing this term was, of course, abandoned. But the fact that the term was introduced and this tensoral structure, lambda g mu nu, was introduced in the equations, it doesn't mean that you can just get rid of it so easily, only because the phenomenological motivation, the initial phenomenological motivation disappeared. In any case, Einstein just abandoned the idea 14 years later in this paper on the cosmological problems of general relativity. Okay, and so this was a situation. It was introduced and then it was just banished by Einstein himself. In any case, as I told you, the fact that this structure has been introduced there, this rho lambda g mu nu, then of course, unless you have a very powerful reason to just cancel it, you have to keep it and try to understand what is its ultimate origin. But in any case, what we have is that this lambda, as we know, which was introduced in this, say, simple-minded way, so to speak, it was actually resuscitated in a more fundamental way 50 years later when Zeldovich realized that the vacuum energy density is something that we can get very easily from the quantum fluctuations in quantum field theory. And therefore, if this contribution is there and it becomes sufficiently large, then of course it causes a big problem, because we know that the observations put tight bounds on these parameters. So the cosmological constant problem, as it is written here, stems from realizing that the effective or physical vacuum energy is the sum of two quantities, not just the rho lambda term, or if you use the lambda term in the original Einstein-Hilbert action, but also the fact that there are some fluctuations, some vacuum fluctuations from quantum field theory, which induce another contribution, which we call it rho lambda induced, and this contribution can be actually very, very large. This contribution, rho lambda induced, is made of two generic terms, which are completely independent in principle. One of them is caused by the vacuum expectation value of, for example, scalar fields, say the Higgs field, and it is associated to the spontaneous symmetry breaking mechanisms, which we have in nature, because we have found the Higgs, and we believe that that this mechanism is it has a reality, a physical reality, right? So this contribution is there. We cannot forget it, and it is a very big one, actually, big as compared to what we measure in observations in astrophysics, okay, when we perform a measurement of the cosmological constant. And then there is, of course, the 0-point energy contributions from all the fields. This is a pure quantum effect. It means that it is proportional to powers of the Planck constant, okay? So we have this contribution, which can be even a classical contribution, but it can also receive quantum corrections. So this potential can be just a classical potential, and then you promote it into an effective potential, which includes quantum effects. So it is a complicated object. And of course, this 0-point energy is also a complicated object because it involves closed loops, bubbles, at any order in perturbation theory. And it turns out that the sum of these two contributions somehow should conspire in order to give a very tiny value, right? Which is the one which we measure, despite the fact that we know that these two values are very big when they are taken alone. So unless we do some very ugly fine-tuning between these two terms, then we expect that the prediction of the vacuum energy is much larger than the one that we measure, okay? So of course, this is nothing else but the famous cosmological constant problem. So as we see, the quantum vacuum is a complicated object. So here you have just a pictorial view of these bubbles, of these vacuum to vacuum diagrams without external tails. So any particle, for example, here I have put an electron and a positron, but you can take whatever pair of particle and antiparticle. They are just fluctuating, and then you have to sum over all the modes, 1/2 h bar omega k, okay? And this sum, of course, it becomes a sum in the continuum, an integral, and it becomes highly divergent. And then you have to cope with the difficulties of this divergence, the normalization, and so on and so forth. So this is only as far as the 0-point energy part is concerned. Then you have to, of course, take care of the effective potential contribution. So in the vacuum energy is a combination of these bubbles, right? Plus, of course, this contribution from the spontaneous symmetry breaking mechanism. So here we have the Mexican hat potential, the Higgs, okay? And of course, this degenerate minimum here is the depth of this potential is nothing else but the value of the vacuum energy from the electroweak sector of the standard model, which you have also to add up to the contribution from these bubbles. So in the end, what we have is that if we consider the various contributions to lambda, right, from different sectors, then we get pure nonsense. Because if we take, for example, as I said, the electroweak contribution, which gives a typical value of for the expectation of the Higgs potential of order of 10 to the 8, 10 to the 9 GeV to the 4th. When you compare with the 10 to the minus 47, which is the measured value of rho lambda, then you get this discrepancy of 55, 56 orders of magnitude. Even if you disregard for a moment this electroweak contribution, of course, you can go to the much humbler QCD contribution, but still, despite it is much smaller, as you can see, it still gives 40 orders of magnitude, 43, 45 orders of magnitude, if you consider the chiral contribution from the expectation value of quark, anti-quark, or if you consider the contribution of the expectation value of the gluons, okay? F mu expectation value. You have also the 0-point contribution from the electron in some standard calculation. Of course, if you go to some typical GATT where mx is of order 10 to the 16, then the fourth power of this is 64, you get 111. When you go to quantum gravity, you have 10 to the 19 to the fourth power, so 10 to the 76. And then is when you get this famous number, 10 to the 123. But this one is not the one which is more worrisome for me. And for me, the most worrisome one is this one, because this one, at least we know it is real, if we believe in the Higgs, okay? Now, of course, we have to move to curved space-time, to quantum field theory in curved space-time. We could try to do it in quantum gravity, but as we know, this is more difficult. So at the moment, we will be more humble and we'll consider just gravity as an external, as a background field, okay? And then from this point of view, what we have is some matter fields which are quantized, and then we attach some external gravitational legs to these diagrams. And this first diagram is the one which precisely gives the contribution to rho lambda. It is a quartically divergent contribution. It is the most serious one, okay? And it is responsible for the 0-point energy of any field, as I was talking before. This contribution in which we insert this vertex here with an arbitrary number of external classical graviton legs, so to speak, okay? So, then what we have is just a renormalization of autogravitational constant, okay, or inverse if you wish. Then, of course, you can put two insertions, and then what you get is a renormalization of the higher derivative terms. This alpha I are just the coefficients of R squared in its different versions, okay? So this is the kind of thing that you get in in this context, in quantum field theory, in curved space-time, you have to cope with these diagrams, and then to give a sense to this one and try to renormalize it in an appropriate way in order to see if it is possible to provide a sensible contribution or prediction for the cosmological term or vacuum energy. Okay. As we know, this diagram here, we perform a naive computation. If, for example, we take some scalar particle of mass m, then by dimensional reasons, what you get is just the quartic power of this mass, okay? Whatever it be the mass of this particle, okay? So if you put a fermion, it also happens the same. It will be the quartic power of the mass of the fermion. So just imagine to put here a top quark with 174 GeV to the fourth power, but you need not to go to the top quark. You can just take an electron and you get a contribution which is many orders of magnitude bigger than the one that we measure. Okay, so it means that we have to do something here, and the kind of thing that we considered long ago was to consider a class of time-evolving vacuum models following this power series here with different powers of the Hubble rate, and then this constant here, okay? And this idea has been proposed from the point of view of from different points of view, but originally here it was proposed having in mind a normalization group equation for the cosmological constant and the vacuum energy. Okay, irrespective of its motivation, on which I will come back to later. Recently, we have tested this idea in the last few years by considering some particular version of this proposal. In particular, we took, for example, for the present universe, the terms which are relevant would be these two ones here. I will just forget about the odd powers of H because it would not be consistent with the general covariance. So if I would take just the first two terms, C0 and C2, then we would get this contribution. You can just normalize it to the value of the Hubble parameter at present. And then what we get is that we get some coefficient, which we call it C2 here, and we call it 3 nu here. And then it is possible, as I will show, to motivate these formulas and even to get a prediction for the value of this coefficient, which behaves as the beta function for the running of the normalization, the running of the cosmological constant. Okay, so we expect it to be small, and we will actually find it small. Okay, so if it is small and the main term, the dominant term, is a constant, then we expect not to depart too much from the standard model, and so we expect that this theory should be phenomenologically sound. Okay. So, as I said, the idea was that...
You have 10 minutes, okay?
Sorry?
You have 10 minutes.
Amazing. So it means that I have to fly. Okay, so then, yeah, sorry. Maybe I tried to spend too much time in the motivation. So what we have is here is this normalization group equation, which we proposed, in which you see that rho lambda runs with some scale mu, okay? And then we have some powers, mu squared, mu to the 4, mu to the 6. And then, of course, what we try to do is to associate this scale to some physical observable. Typically, it could be the Hubble rate, because mu is a parameter of dimension 1, so mu squared can be, for example, linear combination of h squared and h dot, right? When you insert it here and you integrate, then you get this structure here. And a reduced version of it would be one which would include these three terms. So a constant, then a quadratic term, and a quartic term. Of course, the quartic term would only be relevant for the early universe because it could trigger inflation. This inflation would be different from Stravinsky inflation. I will not go into details why, but in any case, as I said, these two terms could play a role for the present universe in the sense that it could predict some evolution of the vacuum energy beyond constant. If nu is small, then this running will be mild and it can be tolerable. It can even be fitted to the data through this parameter nu. And then in a subsequent stage, you can try to use this term here for describing inflation, okay? So this is just some qualitative argument. But recently, we addressed a full-fledged quantum field theoretical calculation, trying to see if we can substantiate this sort of a structure. So this is the paper, and a new one will appear very soon, much more expanded, more detailed. This one is already quite detailed, but the next one it will be even more. So the idea is to start, for example, from some scalar field, non-minimally coupled to curvature. So we have this kinetic term, then we have this non-minimal curvature. I will not consider spontaneity symmetry breaking contributions. This calculation is already complicated. So if we include an effective potential, it will be much more, but it can be handled. At the moment, I will not consider this contribution. I will just concentrate on the 0-point energy contribution. So I take this simplified model, just one scalar field, non-minimally coupled to curvature, and then we compute the classical energy momentum tensor. Then, of course, we take into account the quantum fluctuation. So it means that the field is decomposed into a background contribution plus a fluctuation. Then we define the vacuum energy momentum tensor as the sum of the rho lambda term in the Einstein-Hilbert action plus the fluctuating part of the field, and now I will fly. Then we split the Fourier modes, the fluctuation into the Fourier modes. Then we apply the Klein-Gordon equation. We go to momentum space. We get this equation in terms of the expansion modes. And then, of course, this equation is complicated. It's a linear equation, but this frequency here depends on the scale factor, for example, but also on curvature. Then we have to solve this linear equation. And then what we do is to apply this transformation. Here, we convert this linear equation into a nonlinear one, which is suitable for the WKB approximation. So we proceed to perform a WKB expansion, which is basically an adiabatic expansion. An adiabatic expansion is an expansion in the number of derivatives of the field. And then, okay, so we compute the different adiabatic contributions, which basically can be parameterized in terms of powers of the Hubble rate. And indeed, what we find is that only the even powers remain because of general covariance. And then, okay, we perform the calculation using the creation and destruction, annihilation and creation operator, and so on and so forth. And so this is the expression. And finally, since these modes can be written in the WKB approximation, the 0-0 component of the energy momentum tensor of the fluctuations, which is nothing else but the 0-point energy contribution, is given in terms of this expression. And all these terms, these red terms here are divergent terms. The other ones are convergent. So it means that we have to, we get a divergent expression. We have to renormalize it, okay? And then in order to renormalize it, what we do is just to perform a subtraction of the on-shell value. We subtract the result at an arbitrary scale m.
Excuse me, 5 minutes.
Okay, thank you, George. So then we subtract only the first 4 adiabatic contributions, because these are the only ones which are divergent. Okay, so here in principle you can compute this at any order, but then the subtraction has to be only up to 4th adiabatic order. And then this big formula that I have shown before, after many calculations, it turns out that it can be written in this very compact form here. So this is the renormalized value of the energy momentum tensor of the fluctuations. We put it on the right-hand side of Einstein equations, and then we relate this value at 2 different scales. So this is computed at the scale m, and then we perform a subtraction at 2 scales, m and m0. Then, of course, this will mean to perform the subtraction of the gravitational constant at these 2 scales, rho lambda at the 2 scales, and then the coefficient of this higher order tensor also at these 2 scales. And after some work, what we find is that the expression for the vacuum energy density at the scale m can be related to the vacuum energy density at the scale m0 through this relation, which is quite interesting from my point of view, because you can see that these 2 values of the vacuum energy density are related by this term here, which is proportional to h square. And then there is a higher order contribution, because this is h dot square, h double dot, and so on and so forth, and so on and so forth. So this will be negligible at the present universe, but this one will not. And of course, this takes exactly the kind of a structure that I have mentioned before, in which the vacuum energy is some constant plus some value at some fixed scale plus a term which is proportional to h squared. You see that this coefficient here is the non-minimal coupling, minus 1/6. So it means that if psi would be 1/6, which would correspond to conformal theory, then this term would be 0. It would not run. Okay, this is also expected. You see that also the higher order term vanishes for psi equal 1/6. There is a power 2. Okay. Now the point is that we get this h squared that we wanted. We do not get the h to the 4th power yet, but this can be obtained in a stringy version of this calculation. But since I'm running very short in time, I cannot go into these details. It's something that we have been working with Nick Mavromatos, okay, in a series of papers. Here we have this review paper actually, okay, and we can show that this term appears in this version. So finally, what we get, is what we wanted. So we want that the vacuum energy density behaves like a constant plus a term which is quadratic in the Hubble rate plus higher order contributions, which can be of order h to the 4th power. Okay. Here we have, for example, a prediction of the value of the coefficient nu that, as I was telling you before, which had to be small. Indeed, it is small because apart from details, you can see that this coefficient, if we define the couplings, for example, Chang-Granified theory characterized by the scale mx, then this nu is the ratio, apart from other factors, of mx over m Planck square. So it means that it is a small parameter, okay? So indeed, it is a sensible result. It is just some departure some theory which includes quantum effects on the classical theory around the standard cosmological model, which is characterized by a fixed rigid value of the cosmological constant. Okay, so we can also apply these ideas to inflation, but I will skip all this, and because I want to show some phenomenology of this calculation. This is something that we presented recently in this paper from this year. And what we did is to consider these models in two versions. One is the so-called type 1 running vacuum model. In both cases, here we have type 2, but in all these cases, we have this energy density, which gets the same generic structure, which is a constant plus a term proportional to h squared. And then we can even admit the possibility that there is a coefficient times h dot, which is after all the same order of h squared. We can show that this term also appears, okay? And then once we have this structure, we can compare it with observations. But before doing that, we define this so-called type 1 running vacuum model and the type 2 running vacuum model. What it means that we consider this structure, this running vacuum energy density, and then you can consider that it interacts with matter, in particular with cold dark matter. So there is indeed an exchange between dark matter and vacuum, okay? Of course, if raw vacuum would be a constant, this would be 0, and then we would have just the normal conservation law. But if you have some running with H, this raw dot vacuum will not be 0, and of course then you can compute some non-trivial dynamics here, right? Sorry?
Please conclude, the time is up.
Okay, good. And then, right, and then for the type 2, we have a similar situation, but we do not consider interaction with matter. We consider the possibility that the gravitational constant is changing, and then there is an interchange between the running of vacuum and the running of the gravitational constant without, with matter conservation. So using these models, what we find is, for example, that when we make a plot of H0 and sigma 8, right, these famous parameters which are in tension in the context of the standard model, let us just have a look at this red prediction corresponding to the model in which the gravitational constant is changing simultaneously. The change is just logarithmic, of course, simultaneously with vacuum energy. You can see that the typical prediction for H0 is rather high. Okay, it is in the range that we would like to have, or at least it is closer to the range we would like to have from the local measurements of H naught. And at the same time, the value of sigma H is below 0.8. There are many models in the market in which they can, for example, improve the value of H0, but then they get the prediction of sigma 8, which is overshoots 0.8 by a lot, for example. And then, of course, what you want to have is a simultaneous prediction of the two parameters in the correct range. And indeed, these kind of models achieve to do that. Okay, so I go to my conclusions. Dynamical dark energy is a natural proportional for an expanding universe. The running vacuum model is based on a running lambda term, interaction with matter, or G, and it is theoretically well motivated because I have provided explicit calculations in quantum field theory in which I can show that these models can be constructed. And then these running vacuum models seem to describe better the observations than the lambda CDM, because when we perform an overall fit to the data, which we have done in several papers, then using, for example, information criteria, what we find is that they favor these running vacuum models against the lambda CDM. Apart from the fact, of course, that they solve or at least alleviate substantially the tensions, the sigma 8 and 8,0 tensions. So they provide a consistent solution to the main tensions, and well, these ideas may perhaps signal a connection between the large-scale structure of the universe and the quantum phenomena in the microcosmos. Thank you very much.
Okay, thank you very much. Is there any quick question?
Yes, I have one. Is that? Can I go ahead, Kostas? Or yeah, very nice talk, Jean. Can I ask quickly, what happens if you include the phi to the fourth term?
There is some background noise, Nick. I cannot hear you well.
Can you mute? Yeah, thank you. Sorry. Very nice talk. Can you tell me, can you elaborate briefly what happens if you include the interaction terms phi to the fourth in the quantum field theory? Do you expect h to the fourth terms there, or?
Yeah, of course. I mean, we did not even attempt this calculation because, well, as you have seen, even with just the 0-point energy contribution, which means basically these bubble diagrams at one loop. Okay, so what we consider is just bubbles at one loop. If we would have, for example, interactions like lambda 5 to the fourth, also the bubbles should have four point interactions. Okay, right. So of course this would be complicated, not only because you have to consider the normalization effects on the effective potential, but also because the 0-point energy contribution would be more complicated. Okay, so so yes, in principle, this is something that we should address at some point. But from my point of view, the main thing which I wanted to emphasize here. Sorry, I don't know what happened here. I've lost. Where is my talk?
I can see it on the screen, but
yes,
but that I
cannot see myself. Okay, what happened with my talk? Anyway, yeah, okay. So the point is that, yeah, as you have seen, I am now moving my PDF. You can see that?
Yes, I can see the movement.
Okay, okay, okay. All right. So then, for me, the main result here, perhaps, which I didn't mention, and you gave me the opportunity to mention, is that you see the relation between the vacuum energy density at 2 points, at 2 energy, if you wish, at 2 scales, do not involve quartic powers of the masses.
Right.
And this is something that I have not seen in the literature anywhere.
Right. That's
because you see the main source of trouble for the cosmological constant problem is the fact that you get isolated m to the fourth contribution. This is the kind of thing that you get when you perform the calculation, for example, in the minimal subtraction scheme, which is a very simple-minded calculation, by the way, but in any case, you can do it. And then what you get immediately is m to the fourth. And of course, you take any particle, even the electron mass, except the neutrino, a very tiny neutrino of order 10 to the minus 3 milli-electron volts, okay? Of course, any contribution gives very, very, very large, but you don't get this here. What you get is quadratic contributions, which, of course, by dimensional reasons, because this guy here is dimension 4, they are accompanied by powers of h. So, of course, h is very small, so h square m square is of order precisely of the value of the cosmological constant present. And what you get is just some tiny correction to it, because as I told you, what you get is just a correction to the main term, okay? So for us, this is already important. Now, of course, in the next step, you have to consider what happens when you include the potential, the corresponding effective potential with the quantum effects. And as I said, you have also to combine with a 2-loop contribution to the 0-point energy, because otherwise you will not be able to normalize the whole thing, right? And of course, this is much more complicated, okay? So we we may attempt that, but at the moment, the kind of things that we are doing, apart to present these ideas in a more detailed way in a next paper, what we do is, for example, to consider what is the contribution from fermions, because here I just consider the contribution from one scalar field. It is also interesting to see what the contribution of fermions and see what is the overall effect, okay, on the vacuum energy. The main message, therefore, is that from quantum field theory in curved space-time, what we get is dynamical vacuum energy, dynamical running vacuum energy. Okay.
Thank you.
Okay, thank you. So thank again the speaker, thank again the speaker. And we have a 15 minutes just break.
Okay.
I apologize for the delay. Okay, thank you very much for your talk.
Thank you, George.
Kostas, you should stop the recording during the break, I think.
I see.
Thanks, Joan.